Some basic concepts of chemistry for 11th science. The Gay-Lussac law of gaseous volume. The law states that when the gases combines or are produced in a chemical reaction, they do so in a simple ratio by a volume, provided all gases are at same temperature and pressure. This law states that when the gases combines or are produced in a chemical reactions, they do so in the simple ratio by the volumes, provided all the gases are at the same temperature and pressures. This is the Gay-Lussac law for gaseous volumes. For example, under the same conditions of temperature and pressure, 100 ml hydrogen combines with 50 ml of oxygen to give 100 ml of the water. 100 ml H2 combines with the 50 ml H2 combines with 50 ml oxygen to give 100 ml of the water. Means hydrogen gas plus oxygen gas, it gives the water molecules. 100 ml, this is the volume of hydrogen, 50 ml volume of oxygen, and 100 ml, this is volume of this water molecule. Means 2 volumes of hydrogen combines with 1 volume of this oxygen produces 2 volume of the water. Therefore, according to the Gay-Lussac law of gaseous volume, all these combining volumes of all the gases bears a simple whole number ratio. Therefore, the first is 2, second oxygen volume is 1, and water volume is 2. Therefore, thus it bears a simple whole number ratio as 2:2, 1:2, 2. And this is a Gay-Lussac law. Another example, under the same conditions of temperature and pressures, 1 liter of the nitrogen gas combines with 3 liters of hydrogen gas to produce 2 liters of the ammonia gas. This reaction is represented as, this is a nitrogen gas, hydrogen gas, and this is ammonia gas. According to this example, 1 liter of this nitrogen combines with 3 liters of this hydrogen to form 2 liters of the ammonia. Therefore, the volumes, in terms of volumes, these reactions are represented as 1 volume of nitrogen, 3 volumes of hydrogen, and 2 volumes of this ammonia are formed. Therefore, this bears a simple whole number ratio, and this ratio is 1:2, 3:2, 2. It is represented as 1:3:2, 2. And this is the Gay-Lussac law. This law is important in case of the gaseous volumes of the substances. The next law is the Avogadros law. This Avogadros proposed that the equal volumes of all the gases at the same temperature and pressure contains equal number of the molecules. Avogadros law states that the equal number of the volumes of all the gases at the same temperature and pressure contains equal number of the molecules. Means, if we consider the reaction of hydrogen and oxygen, to produce the water vapors, in this case, hydrogen gas combines with oxygen gas, it produces the water. This example is similar to that of the Gay-Lussac law. 2 volumes of hydrogen, 1 volume of oxygen combines together forms 2 volumes of this water, according to this Gay-Lussac law. in Gay-Lussac law there is a consideration of these volumes, and the 2n molecules of this hydrogen combines with n number of the molecules to forms 2n molecules of this water, and this is the according to the Avogadros law, because Avogadros law proposes that equal volumes of all the gases at the same temperature and pressure contains equal number of the molecules. Therefore, 2 molecules of hydrogen combines with 1 molecule of oxygen forms 2 molecules of this water. Therefore, Avogadros could explain above result by considering the molecules to be polyatomic molecules. This is formation of this water. This is the polyatomic molecules, that is the triatomic molecules, 2 hydrogen and 1 oxygen is present, and this law is also important for chemistry. Next is the atomic and molecular masses. In this atomic and molecular masses, the concept is very simple. The first is atomic mass. Atomic mass is the mass of an atom. Simply, atomic mass is the mass of an atom, and this mass of an atom is very small. For example, the mass of one hydrogen atom is 1.6736 into 10 raised to minus 24 grams. An atom of the carbon-12 is assigned a mass of exactly the 12 atomic mass unit. This atomic mass unit is termed as a AMU, and all other atoms of other elements are given the relative atomic mass to that of the carbon-12. Means this carbon, the atomic weight of this hydrogen is determined by the 1.6736 into 10 raised to minus 24 grams. Carbon 12 is considered as assigned as a 12.000 atomic mass unit, and all other big elements are calculated by using the relative masses to that of the carbon 12, and the atomic masses are expressed in AMU atomic mass unit. For example, 1 AMU is defined as the mass exactly equal to the 1/12 of the mass of one carbon-12 atom. 1/12 mass of one carbon-12 atoms. Therefore, 1 divided by 12 into 1.992648 into 10 raised to minus 23 grams. This is equal to the 1.66056 into 10 raised to minus 24 grams. Means 1 AMU equals to the 1.66056 into 10 raised to minus 24 grams. Recently, AMU has been replaced by the unified mass unit called Dalton. Symbol is U or DA. And there is a U means unified unit. By using this atomic mass formula, we can determine the atomic mass of any element by considering 1/12 mass of the C12 carbon atom. Next is the average atomic mass. The sum of the masses of its isotopes, each multiplied by its natural abundances, is called average atomic mass of an element. Means there are, suppose, for example, in this case there is the isotopes of the carbon C12, C13 and C14. Their atomic masses are 12, 13.00353, C14, 14.00317, but their relative abundances are variables. In case of the C12, this is high percentage, 98.892%. There is a natural abundance of the C12. For the C13, 1.108, and C14 is 2 into 10 raised to minus 10. This is the natural abundances. If we multiply this natural abundances with these atomic masses and take the average of the atomic masses, we get the average atomic mass. For example, the average atomic mass of the carbon equal to, this is the 12 into 98.892 divided by 100, because this is a percentage, plus 13.00353 into 1.108 divided by 100, plus 14.00317 into 2 into 10 raised to minus 10 divided by 100, and this is equals to the 12.011 unit. And this 12.011 unified unit, this is the average atomic mass of that carbon atom, because there are the three naturally occurring these isotopes, and their isotopes atomic masses are multiplied by their natural abundances and take the average. This is the average atomic mass. Then the molecular mass. Molecular mass of the substance. Molecular mass of the substance is the sum of average atomic masses of the atoms of an element which constitute the molecule. Molecular mass, in a molecule there is each molecule contains the different atoms. They combine together and forms the molecule or the polyatomic molecules. Each atoms having the different isotopes and taken their average atomic masses and calculating their molecular mass. This is the process for calculating the molecular masses. Another definition, molecular mass of the substance is the mass of one molecule of that substance related to the mass of one carbon-12 atom. Mass of one carbon-12 atom, or the masses of the substances is the sum of average atomic masses of an element which constitute that molecule is called as a molecular mass. Another simple definition, molecular mass is defined as it is the sum of atomic masses of that atoms present in that molecule is called as a molecular mass. It is obtained by multiplying the average atomic mass of each element by that number of its atoms and adding them together. For example, in case of this carbon dioxide, there is a one carbon atom, therefore 1 multiplied by average atomic mass of this carbon, plus 2 oxygen atoms multiplied by average atomic mass of this oxygen. Therefore, 1 into 12U plus 2 into 16U, this is equal to the 44 unit. Unified unit, this is the molecular mass of this carbon dioxide. Some more examples taken here, their molecular masses. First is a water molecule. Water molecules, there is a 2 hydrogen atoms, 2 into 1U plus 16, 1 into 16U, that is equal to the 18U. This is the 18 unit, or 18 is a unified unit, atomic unit is the molecular mass of this 1H2 molecule. Similarly, in case of the chlorobenzene, 6 into 12U plus 5 into 1U plus 35.5 into U into 1. 6, this is the carbon, hydrogen, and this is the 1 chlorine. It is equal to the 112.5 unit. Third, sulfuric acid, H2SO4. And this sulfuric acid equals to the 2 hydrogen atoms. 32 is a sulfur, 1 sulfur. 4 are the oxygen atoms multiplied by their average atomic weight. 16 unit equals to the 98. These are the 3 examples of calculating the molecular mass of this H2O, chlorobenzene, as well as sulfuric acid. The next one is a formula mass. The formula mass is different to that of the molecular masses, because the formula mass of a substance is the sum of atomic masses of the atoms present in the formula. Sum of the atomic masses of the atoms present in the formula. This is the formula mass. And the molecular mass, this molecular mass means there is a average atomic masses, sum of the average atomic masses of an atom present in the molecule. This is compared to the 112 mass of carbon 12 atom. For example, some substances do not contain the discrete molecule as the constituent units. In such compounds, cationic and anionic entities are arranged in a three-dimensional structure. Cations and anions are arranged in the three-dimensional structure in an actual molecule. They does not present in the discrete molecules. Then we can consider this molecule as a formula mass. For example, sodium chloride. The one sodium ion cation is surrounded by the 6 chloride ions, all the same distance from it and vice versa. That is, each chlorine atom surrounded by the 6 Na plus ions and one Na plus ions surrounded by the 6 Cl minus ions in a three-dimensional network. Therefore, the NaCl is just a formula used to represent the sodium chloride, although it is not a molecule. This is a formula mass of the NaCl, but they are surrounded by one sodium by the 6 chlorine and one chloride ions by the 6 Na plus ions. This is the vice versa. Hence, the term formula mass is used for such ionic compounds instead of the molecular mass. We cannot consider this three-dimensional network. At this time, we consider their formula masses, but not of this molecular mass. And this is the difference between formula mass and molecular mass. Next one important concept is a mole. The one mole The 1 mole is the amount of a substance that contains as many entities or the particles as there are atoms in exactly 12 grams or 0.012 kilograms of the carbon 12 isotope. Let us calculate the number of the atoms in 12.0000 grams of the carbon 12 isotopes. 1 mole is the amount of the substance that contains as many entities or the particles as there are atoms in exactly 12 grams of the carbon 12 isotopes. For example, the mass of one carbon 12 atom equals to the 1.992648 into 10 raised to minus 23 kilograms. Therefore, the mass of 1 mole carbon atom equals to the 12 grams. Mass of 1 carbon atom 1.992648 into 10 raised to minus 23 grams, and mass of 1 mole of the carbon atoms is 12 grams. Therefore, number of atoms in 12 grams of the carbon atoms, carbon 12 equals to the 12 grams per mole divided by 1.992648 into 10 raised to minus 23 grams per atom, and this is equal to the 6.022 1367 into 10 raised to 23 atoms per mole, and this number is called as a Avogadros number. Thus, 1 mole is the amount of the substance that contains 6.0221367 into 10 raised to 23 particles or the entities such as atoms, molecules or the ions, and this number is termed as a Avogadros number. Here note that this name of the unit is a mole. This unit is a mole, and unit is represented symbolic format as a mole, MOL. This mole, it is a unit in symbolic format, and this is name for this unit is a mole. Next is a molar mass. The mass of 1 mole of the substance in grams is called as a molar mass. Molecular mass, it is the average sum of the atomic masses of an atoms present in that molecule, and this is considered to the 1/12 mass of an carbon-12 atom. This is the molecular mass. And molar mass, the mass of 1 mole of the substance in grams is called as its molar mass. This molar mass of any element in the grams is numerically equals to the atomic mass of the element in U. Therefore, element hydrogen, carbon, oxygen, 1, 12 and 16 U atomic masses, molar masses in grams per mole, 1 grams per mole, 12 U, it is a 12 grams per mole, and it is a 16 U, 16 grams per mole. Similarly, the molar mass of any substance existing in a polyatomic molecule in grams is numerically equal to its molar mass, molecular mass, or formula mass in U. Let us see here. The molar mass of the substance existing in a polyatomic molecule in a grams is numerically equals to, it is a numerically equals to the molecular mass and formula mass in U. Therefore, polyatomic molecule substances oxygen, oxygen molecule, H2 molecule and NaCl molecules. Formula mass and molecular mass are same in their that of the unified unit. They are converted into their molar mass as a grams per mole. 32, 18, 58.5 equals to their grams per mole. Oxygen 32 grams per mole. H2O 18.0 grams per mole. NaCl formula mass 58.5 grams per mole. And this is a molecular or formula mass. They are expressed in terms of unified unit. Molar mass expressed in grams per mole. Therefore, molar mass of the oxygen equals to the 6.022 into 10 raised to 23 atoms per mole into the 16th unit, unified unit per atom into the 1.66056 into 10 raised to minus 24 grams per unit equals to the 16 grams per mole. This is the Avogadros number, and this is the 16 is the atomic mass of this oxygen. 1.66056 into 10 raised to minus 24 grams per unit. It is the weight of the hydrogen, and after calculating this value, we get there is a 16.0 grams per mole. This is a 1020. It is not a 1020. It is a 10 raised to 23, and it is a 10 raised to minus 24. This is the concept of molecular mass. The last point is the moles and gases. From the Avogadros law, that 1 mole of any gas occupied a volume 22.4 dm cube at standard temperature 0 degrees Celsius and pressure 1 atmospheric pressure at standard temperature and pressure STP. The volume of 22.4 dm³ at STP is known as a molar volume of the gas. Means the 1 mole of the any gas occupied a volume 22.4 dm³ at the standard temperature 0 degrees Celsius and the pressure 1 atmospheric pressure. At this time, the volume is 22.4 dm³ at STP is known as a molar volume of the gas. This number of moles of the gas are calculated by using the formula number of moles of the gas N equals to the volume of the gas at STP divided by molar volume of the gas. And this molar volume of the gas value is a 22.4 dm³. Therefore, volume of the gas at STP divided by 22.4 dm³ per mole. Therefore, number of moles equals to the number of moles into the Avogadros number. This number of moles multiplied by the Avogadros number, we get the number of molecules. Number of molecules equals to the number of moles multiplied by the Avogadros number. And in this case, number of moles are calculated by using the volume of the gas at STP divided by 22.4 dm³ per mole. Nowadays, the pressure STP, the standard pressure is to be 1 bar. Standard pressure the standard pressure is a 1 bar. Under the new standard temperature and pressure, these conditions, the standard temperature and pressure, under these conditions, the molar volume E of the gas is 22.71 liter per mole. And under this standard temperature pressure contains, there is a 22.4 dm³ per mole, and according to the 1 bar pressure 22.71 liter per mole. And this is the moles of the gases. This number of moles of the gas is calculated by using the mole triangle, and this mole triangle is represented as, this is the mole triangle. In this case, the number of moles, this number of moles are calculated from the volume occupied by the gas at STP in dm³. If this volume is divided by the 22.4 dm³, we get the number of moles. If this number of moles are multiplied by this volume 22.4 dm³, we get the volume occupied by the gas at STP in dm³. Second one, this mass of the substance. This mass of the substance are divided by the molar mass, we get there is a number of moles. And this number of moles are multiplied by the molar mass, we get the mass of the substance. Third part, the number of fundamental particles, they are interconvertible into the number of moles, as this number of moles are multiplied by the Avogadros number, we get the number of fundamental particles. And this number of fundamental particles are divided by the Avogadros number, we get the number of moles. And this is the mole triangle, which is useful for the conversion of number of moles into the mole mass of the substance, or number of moles into the number of fundamental particles. And third part, number of moles into the volume occupied by the gas at STP in dm³. All these three quantities are also interconvertible into this number of moles by using this mole triangle. Thank you.